Okay, ji. So, Bismillah ar-Rahman ar-Rahim. So, let's start today's lecture. This is our second module, and this module will span over around about 4 classes, three to 4 classes. And the name of this module is Stress and Strain Transformation. And we'll discuss some more things in this module also, which are related to this transformation. In our previous lectures, in our module 1, we discussed about the combined stresses, and especially about the combined normal stresses. How to combine normal stresses? Okay, if a number of actions are acting on a body, and those actions may be which produce normal stresses are axial force, bending moment about one axis and a y-axis, and bending moment about z-axis. So if these three forces are acting simultaneously, one axial force and one bending moment acting on a body, or two bending moments are acting on a body. Okay. So two bending moments acting on a body, so that case was related to unsymmetrical bending. Because we resolve the bending moment applied on a body, there is no axial force, and we resolve the bending moment into its rectangular components into two bending moment about the principal axis. Okay, and we discuss how to deal with the cases if the principal axes are known to you and the cases if the principal axes are not known to you. So we discuss all those things. And let me tell you that in all those cases, we were getting stresses in a particular direction, at a particular point in a particular direction. Those formulation we already discussed for the combined stresses, for the short prismatic member, for the unsymmetrical bending. All those formulations were giving us stresses at a particular point in a particular direction. Okay, the direction was important. Okay, that was not giving us that. Let's suppose if I'm saying that give me the stresses at an inclination of this with the x-axis or inclination of this with the y-axis. So the case was not like that. Okay, so that was a fixed direction. We are getting stresses in a particular direction, and that was the x direction. In all the cases, the normal stresses we are getting were in the x direction. Okay, so there are cases if we may require, and why we require those things, the stresses may be required in some other orientation, and the today's lecture about the calculation of stresses in some other orientation. Okay, why we require we require those stresses, so we'll discuss that in today's lecture. So before going to discuss that, so this is basically the total content of this module, and we'll cover this whole content. Let me show this view. We'll cover this whole content in 3 to 4 lectures. Okay, so first we'll talk about the stress at a point, how to represent the state of stress at a certain point in a certain direction. So first we'll discuss this because this is important. You should know that how to represent stresses in a particular point in a particular Cartesian coordinate system. So this is important. Then we'll discuss the stress transformation, and there are basically two methods. One is analytical method, and the other one is a Morse circle. Okay, analytical method. So we'll discuss today the analytical method of stress transformation. In our next class, we'll discuss this Morse circle method of the stress transformation. In the next class, we'll discuss the strain transformation, and in the next class, we'll discuss the relation between Lassig constants and Ferrier-Theodis and these things. Okay, and maybe we can have some mixing of the articles depending upon how we go with the lecture. So these are the topics which we will cover. So let's first cover the stress at a point. This is, let's suppose this is a body, this is a three-dimensional body which is acted upon, which have some constraint. You can see this is a hand support, this is a fixed support, this is a roller support, and this body, this three-dimensional body, is acted upon by a bending moment about the z-axis, bending moment about the x-axis, a force in the y direction, and so on and so forth. There may be some uniformly distributed load, some varying load, and acting on this body. So to represent the state of stress at a certain point within this body, we just take a differential element. Okay, this is a differential element. We take it out. This differential element is in the x, y, and z direction, and this is the enlarged view of this differential element. This is a small. This is just representing a point. Again, this element is representing a point. Okay, because this is a differential element. This direction, this is you can see this is x-axis, this is y-axis, this is z, and this is x-axis, this is along x-axis, this is along z-axis, and this is along y-axis. This distance is supposed to be equal to dx, this is equal to dz, and this distance is equal to dy. Okay, so this is differential element. This is a cuboid element. Okay, an element, a three-dimensional element having different dimension may have same or different dimensions, so those are differential dimensions. Okay, so approaches to zero. So this element, which is a three-dimensional element, has 6 faces. Okay, you can see 3 faces of this element. Okay, this face is named as x phase. Why this is named as x phase? Because its perpendicular is x direction. Okay, this phase, the top phase, is named as y phase. Why this is called y phase? Because its normal is y, and this phase is z phase because its normal is z. Okay, so a phase or an area is named with its perpendicular. Okay, this is general rule. Okay, so this is x phase, this is x phase, this is this is x phase, this is y phase, this is z phase. So you can see these 3 phases, and there are 3 more phases. Like if you have x phase, then you have minus x phase. If you have a y phase, then you have at the bottom a minus y phase, and if you have a z phase, then you have a minus z phase, or you can name phase as an area. Now there are possibly on an area you can have in a Cartesian coordinate system, you can have 3 stress components. These are known as stresses, are the stress components. So if you have an area, so there is a possibility that a normal stress component may act. This is perpendicular to the area, and there is a possibility that in this direction along the z-axis a shear component, because this is called shear because this is parallel to the area. So any stress which is parallel to the resisting area is a shear stress, and this area, this stress component is also, this is in the y direction, and this is also a shear. So on a single phase you are having 1 normal component and 2 shear component in the y and z direction, or in the Cartesian coordinate system along the Cartesian system, okay, coordinate system. Similarly, you have this y phase. So on this y phase you have a normal component. I will discuss this in detail in these subscript in detail, but you have a normal component and 2 shear component. This is in y direction, so this is in x and this is in z direction. And on this z phase you have a normal component and you have shear in the y direction and shear in the z direction. So on each phase you have 3 stress component possibly. Okay, you have possibly 3 stress component. Now there is a way to represent these components. These are represented with just to identify that its location, its direction. So it's necessary to just give it a proper name. Okay, and just the name is like represented with two subscript. First is the symbol, which for the normal case is sigma. Like you can see, this is normal stress, this is normal stress, this is normal stress. All of them are represented. There are three normal stress. So all of them are represented with what? With sigma. And you have shear stress. So all shear stresses are represented with tau component. Now there is a rule for this subscript, that the first subscript represent the plane on which the stress is acting, the phase or the plane on which the stress is acting. The first subscript, like you can see, for all these three components, the normal and the two shear, the first subscript is x, 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 and x. Okay. And the second subscript show the direction of stress. First subscript, the plane on which it is acting. Okay, so since this is x plane, so first subscript is x. The second plane, the second subscript shows the direction of the stress. This is the direction of the stress, and you can see that this is along the x-axis. Okay, this is x-axis, so this is also x-axis. So this is represented as sigma xx. And similarly, this stress, the first subscript is x because this is acting on x plane, and the second is y because this is acting in y direction. You can see the direction y. This is y direction. Okay. Similarly, this one, the first subscript is x because it is acting on x plane, and the second subscript is z because it is acting in the z direction. This is z direction, so this is z direction. And similar is the case for all other gases. Here you can see sigma yy because it is acting on y plane in the y direction, tau yx acting on y plane in the x direction, tau yz acting on z plane in on y plane in the z direction, and similarly for this z case also. Now there is one thing you must note, that for all normal stresses, the subscript are same, both subscript are same, because the plane and the direction of stress are coinciding with each other. Plane mean the normal to the plane. Okay, so the normal stress is always having two similar subscript, and the shear stresses have subscript, different subscript. Okay, so this is normal stress, these are normal stress. So for brevity, to have a short writing, so usually this normal stress is represented with a single subscript. There is no need because both are same. So if you just write x, so it means that both are x. Okay, so this is a normal stress is in x direction, and obviously it is on x plane. Okay, so this is sigma x, sigma y, and sigma z. So usually it is written like this one. Okay, and the shear must be with two subscript because they are different. Okay, they are different stresses. So if they are different stresses, then they must have the two subscript. Okay, acha. Now, how many stress components are there? How many stress components? So here you can see that you have three components. Total are 9 components. And there are 3 more phases on which 9 more components are acting. So total stress components are how much? So this is next slide. So total stress components are 18. 18 stress components. Okay. But not all of them are independent component. Some of the stress components are dependent on other. Okay, not all of them are independent. Okay, these 18 components are not independent components. As equilibrium requirements, some of them are dependent on the other stress component. Okay. One dependency is that on plus x phase, the stress component are same and opposite on the negative x phase or x plane. Okay, if you have stress component on this, like this is sigma xx, this is tau xy, and this is tau xz, so you have stress component on the other phase. Here you can see only normal, the rest of them are not visible, so it's for clarity I haven't shown those components. Okay, so those are like, if you have a shear in this direction, then on the negative phase you have shear in the other direction, and if this is acting in upward direction, then there is a stress acting in a downward direction. Okay, so that is the requirement of the equilibrium, that on the x plane the stress component must be same and opposite to the stress component on minus x plane, and similar is the case for y. For y, the stress component are same as but opposite on this negative y phase, so they are same as this positive y phase, but in opposite direction. Okay, so now we reduced with this, we reduced this 18 stress component to 9, because 9 are similar to those to the other 9. So if you know the 9 components, then you can say that the state of stress at this point is known to you. Okay, the state of stress at this point is known to you, but there are some more dependency also in this case. Other dependency you have studied in your mechanics of solid 1, that the horizontal shear is accompanied by vertical shear, or you might have studied that in your mechanics of solid 1. You can prove this is an equilibrium requirement. You can, using equilibrium requirement, you can prove that if you have, like, if you have a two-dimensional state of stress like this one, so if you have a shear stress on this plane, on x plane, this is vertical shear stress, so it must be accompanied by horizontal shear stress. Okay, this is vertical shear stress, you can see vertical, so it must be accompanied by horizontal shear stress, and the vertical shear stress is same as the horizontal shear stress. In magnitude they are equal to each other. Okay, and this is also the equilibrium requirement. Okay, this is the equilibrium requirement. Okay, so here you can see I have shown the same stress component in the same color, like this tau xy, which this is a shear stress acting on x plane in y direction, and this one is a shear stress acting on y plane in x direction. So they are same in magnitude but different in direction, obviously. Okay, this one is the direction of the shear is like it is taken from its effect. This one is producing a counterclockwise counterclockwise couple, and these two are produced clockwise couple. This one, if you see this as like a couple, so we say that this is a shear which is producing a counterclockwise couple, and this is producing a counter, and it is always like this. Okay, so this is like, this is x plane and this is y plane. So this is x plane, this is tau xy, and this is tau yx. Since they are same, so we just say they are tau xy. Okay. Tau xy is equal to tau yx. So this stress component is equal to this stress component. Similarly, this stress component, this is tau xz, is equal to tau zx. If you just exchange the subscript, so both are then equal. Similarly, this tau yz is equal to tau zy. So I have written it. So total are, out of those 9, now 18. So 18 then reduced to 9. So out of those 9, so 3 were normal components, sigma xx, sigma yy, sigma zz, and 6 were shear components. So out of those 6 components, total are 9 component now. So out of 9, 3 are normal and 6 are shear. You can see 3 or 2 plus 2 plus 2. So out of those 6, 3 depends on other 3.
Sir,
you can say they are same. You have any question?
yes, sir. Sir, if these 18 are reduced to 9, so is it possible that these also reduced to 3?
If so, what are same?
Sir, you
What?
told that the 18 are reduced due to the opposite signs reduced to the 9. So
Yes.
isn't it possible that these are so 9 reduced to 3 or 6
No,
because it
no,
are
no.
same different directions.
No, no, I'm just talking about the same thing, that how and how much you can reduce it. Okay, so I'm talking about that one. So if you have this using these two basic equilibrium requirement, so you can reduce the normal six. There are, if you just think about this 18, so 18 components out of 18, 6 are normal and the remaining 12 components are shear. So out of these 6 component, equilibrium requires, the first equilibrium condition requires that the 3 normal are same as the other 3 normal, so the normal are reduced to 3. Okay, and the shear are, they are dependent, 6 are dependent on the 6, so reduced to 6, and 6 further reduced to 3 components, because 3 are then dependent on the other 3 components. Okay, so finally you have 6 independent component to specify the state of stress at a point in a body, at a certain point in a body. And those 6 components, you cannot reduce it from this. They are independent component. They do not depend on each other. Sigma XX, sigma YY, sigma ZZ, tau XY, tau XZ, tau YZ. So 3 normal components and 3 shear components. So if you want to completely specify the state of stress at a point in a body, then you have to specify these 6 components.
Hello?
I think sir got disconnected.
Hello.
What?
Yes, I think.
Sir, your sound was breaking.
समझ गए पूरा? आपकी आवाज मुझे साफ नहीं आ रही.
Sir,
Sir, you are
Stasha, sir,
flexible.
Yes, sir. Yes,
yani
sir.
akşam zaman kaçıyor, sir. Avazım बनशेव, sir.
हाँ. अच्छा जी. So finally you require 6 stress component, 3 normal and 3 shear, okay, to specify the state of stress in a body in a 3 dimension. Okay, now for 2-dimensional state of stress, if let's suppose some of the phenomenon are represented as a 2-dimensional state of stress. So for 2-dimensional state of stress, like if you are not having any kind of stress in z direction, any stress with a subscript z, if you omit this, if you say this is equal to 0, like sigma zz is 0, tau xz is 0, tau yz is 0, then you left with what? You left with 3 stress components. So for 2-dimensional state of stress, 3 independent components are required. For 3-dimension, you require 6 components, but for 3, if you just max 0, this one, and this one, so then you left with these 3 components, sigma x, sigma y, and tau xy. Okay, and I've shown it with a single subtract the normal stresses. Okay, so for 2-dimensional stress, you require these components. Then there are certain phenomena which you can represent with a 2-dimensional state of stress, like the state of stress at axially loaded member. You can represent it with a 1-dimensional state of stress, because the only stress acting in the x direction. Okay, so this is a 2-dimensional state of stress, but the stress is acting in a 1 direction, and there is no shear stress acting, and there is no stress acting in the y direction. This is y direction, so there is no stress acting in the y direction. Okay, so this is an if you have an axially loaded member, then this is the state of stress. If you pick any point from the body, and if you want to show the state of stress, rest of the stresses, all of the components, the 5 other components are 0. You have only sigma xx, and all other components are 0. For beam, you know that beam is subjected to shear force and bending moment. You know this. Shear forces produce horizontal and vertical shear stresses, and the bending produce normal stresses in the x direction. This is the thing. Okay, so 2 forces are acting. One is producing the normal stress in the x direction, and the other one is producing shear stress. So this is beam element. Okay, this is beam element. You have stress, the normal stress acting in the x direction, and you have the shear stress acting. Okay, shear, as you know, this is equilibrium requirement, that vertical shear is accompanied by horizontal, or horizontal shear is accompanied by equal and opposite vertical shear. Okay, opposite mean its sense is opposite, like if it is producing clockwise or a counterclockwise effect. Okay, so in the case of beam, there is no vertical stress, like you cannot have any sigma y, because beam is not, though the load are acting in the y direction, but they are producing no stresses in the y direction. The lateral forces are producing bending moment, and bending moment are producing the stresses in the x direction. Load is acting in this direction, but stress is producing the x direction. Okay, so this is a beam element. This is an axially loaded element. Okay, and this is a beam element. So beam, any beam can have a state of stress. So you will have to just calculate what is the value of sigma x and what is the value of tau xy. And this is, you can use the bending formula. Okay, and this you can use the shear formula VQ by IB. Okay, you can calculate this with the shear formula. And the sign convention, as a sign convention, tensile normal stress and shear stress producing clockwise effect are considered as positive number. Like this couple is producing a clockwise effect, so this is considered as a positive shear, and the shear acting on x plane is producing a counterclockwise effect, so it is considered as a negative shear. And similarly, the tensile stress are the arrow showing, or the forces showing represented as an arrow away from the element, so those are considered as a tensile stresses, and those are positive number. And the compressive stresses are represented as a negative numbers. Okay, so this is the sign convention for the stress. Okay, you have the shear component and you have the normal stresses. So the normal stresses are obvious. Your tensile stresses are positive and compressive stresses are negative. And shear stresses producing clockwise effect are positive and producing counterclockwise effect are negative. So these are our sign convention for the state of stress. Okay, for the state of stress. Okay. Now coming to the stress transformation, this we were discussing the stress at a point, how to represent a state of stress at a point.
Sir, where can we find such a point which is subjected to a lot of stresses and a lot of forces?
Here can we apply that? So we are discussing these things. So this was just the showing how to show the state of stress. A number of forces may be acting in x, y, z direction, and you will have to show the state of stress. What is the state of stress at this particular point? Because you need stresses for design. Okay, you need stresses for design. Okay, you should know whether the state of stress at this particular point will cause any failure of the body or not. So you need the state of stress. And when you calculate all the stresses, then you can play with this one. If all the 6 components are in axially loaded, the 1 stress component, in B the stress component, in 2-dimensional general element the 3 stress components. If they are known to you, then you say that the state of stress at this point is completely known to you. You can play with the state of stress, and how to play with the state of stress, how to calculate stresses in different direction to know this point is safe, this point will cause any failure of this body or not. And this point must be the critical point within the body. Okay, now this must be, if you want to design a body for a certain forces, then you will have to pick the most severe condition of that. Like if you have a cantilever beam and the cantilever beam is subjected to vertical loading, then the severely stressed location is a fixed end. So you will have to go to the fixed end and pick a point from the fixed end and then analyze that point to get whether this point will cause any failure. So this is one of the objective of this module also that will discuss the failure theories. When we say that failure will be initiated, okay, in the design, one thing is that you see the failure. But if you are designing something, then when you will say that this thing will fail. Okay, so we'll discuss that one in more detail. So the formula, as I've told you, the formula used for determination of stresses, like the Fleger formula, the combined stress formula, the unsymmetrical formula, they give stresses, normal and shearing stresses, the normal and shearing at a point in a particular direction. These formulation give stresses in a particular direction. Okay, they are not giving you stresses in any direction. Like you are getting stresses in X direction, so X direction. If you require the stresses in some inclination, then you cannot use those formulation. Those will give you in a particular direction. So that was important. So stress in other direction that may be required. Why we required stress in some other direction? So there could be two reasons, two important reasons. Okay. The computed stress, like when you compute it using those formulation, may not be the maximum stress, and maximum stress will be required for design. When you calculate, the calculated value may not be the maximum, and since the maximum stresses are required in the design, so the calculation is necessary, that you may be able to calculate the maximum stress. So for this, the stress transformation is required. You need to transform stresses from one plane. Transformation does not mean that it is transformation from one point to the other point. No, this transformation is the transformation from one orientation to the other orientation at the same point. Okay, at the same point, from one orientation to the at the other orientation. So let's talk about this first bullet, that the stresses may not be the maximum stresses you are calculating. Like, let me represent this with this one. Okay, always crack is produced perpendicular to the normal stress. When you just apply normal stresses to a body, so the crack is produced normal to the, or in the case of if the shear stresses are applied, so along the shear plane the stresses are produced. Now here you can see at point A, this is the state of stress. Why this is the state of stress? Let me show you. This is a beam. This is a concrete beam, and you can see the cracks in this beam. When you load this, so these are the cracks, you apply a uniformly distributed load. Let me draw the shear force and bending moment diagram of this beam. Let me draw. This is shear force diagram. This is midpoint. Okay, this is midpoint. And this is bending moment diagram. This also. This midpoint. This is like, this is midpoint. Okay, so this is coinciding. This point is a zero shear point. Okay, and this is the maximum. So here you can see from the bending moment and shear force diagram that the bending moment is maximum in the mat span and the shear is maximum in at the support, and you know this. Okay, this is the shear force and bending moment diagram. Now at this point A, there is no shear acting. The only force acting is the bending moment. Okay, so here there will be, at this point there will be no shear in this beam. The only force acting will be this, like this will be subjected to a pure bending moment. There will be no shear stress. So the state of stress will be like this. There is no shear, so this will be the state of stress at this point A. And when you just applying this stress, so what will happen? A crack will be produced like this. And when you increase the bending moment, so the sigma x will increase, and what will happen? When you increase the load, bending moment will increase, and finally a crack produce. So this is the crack. So it is obvious that the crack is produced perpendicular to this one. Now coming to this point, where both shear and bending moment are acting. At this point B, there is shear and this bending moment. So here you can see the state of stress is like the bending moment is producing the axial stress, and the shear force are producing shear stresses at this point B. Now here you can see the crack is like moving towards the mid of the beam, towards the center of the beam. So this is like you have, what's the reason of this? Why it is like if you have this, so there is a possibility that the stress may be maximum in this direction, like at inclined direction. That's why the crack is producing the inclined direction. Okay, this is concrete, and concrete is very weak in tension. So the crack might have produced because of the stresses in this direction. Okay, then this is not the stress causing crack at this point B. The stress at some inclined direction, which was probably the maximum stress. Okay, so that must be, you must know, or you must be able to calculate that value. Okay, so this stress is not, so this is the inclined direction might be a greater value than sigma x. If sigma x is maximum, the crack produced must be like a vertical crack. But sigma x is not maximum. At some inclined direction, the stress is maximum. Okay. So how to calculate that? Okay. And what is the orientation of the maximum plane? Okay. We'll discuss that in today's lecture. Okay. The next is point number C, and here you can see a crack like a very inclined, a clear inclined crack. Here at this point C, here you can see at the support, the stress is zero, the bending moment is zero, and the shear is maximum at the support. Okay. The bending moment is almost zero at this support, the bending moment, there is no bending moment at the support, the bending moment is zero. So this is zero, and the shear is maximum. So this is a point C, there is no axial stress, and only shear stresses are acting on this point. But the crack is in this direction, so there is a possibility that the normal component, there must be a normal component in this direction at some inclination which have caused this crack. Okay. So the first component, the first thing is that the computed stress may not be the maximum stress. These are the computed tau x, y, sigma x, and these are the computed stresses. They may not be the stress, and maximum stress will be required for design. Okay. The plane on which the stresses are known may not be the critical one. There is another solution that, okay, this must be the maximum stress, but the plane on which they are acting, like this is an x plane, this is a perpendicular plane, so this plane may not be the inclined plane. Like you can have two wooden logs, they are connected to each other like on an inclined plane, and they are glued to each other. Okay, so you need what you need these stresses, like this stress may be, and in this case will be less than this one, but you require this stress. You do not require this stress. Okay, this is higher, but you do not require this one. You require this for the design of this glue connection. You require this normal component, and you require this shear. You can see the shear component and the normal component, because you want to do the design of this glue. Okay, and the glue is developing this is subjected to these kind of forces. So you need to have this one, the normal, and this one, and then if you know these stresses, and you can select appropriate glue which you can apply here at this location to avoid failure. Okay, so this is the case. This is the case in which we may require the stresses at some other plane. Okay, and this a problem is also in our today's lecture. Maybe if we are able to complete this in today's lecture. Okay, so this is why we require to calculate stresses at some other orientation. Okay, or in some other direction. Now let's talk about the formulation. the stress transformation, the formulation of the stress stress transformation. Okay, so stress is a tensor quantity as it is associated with area on which it acts, in addition to magnitude and sense that are required for vector. Vector require what? Vector require magnitude and sense mean the direction. So vector required, but stress is a higher order quantity, higher order than the vector quantity. Okay, as it requires, it is associated with the area vector also. It is associated. So stress is like if you have force acting on an area, force per unit area. So this is the product of what? This is the you can say the product of a product of a stress quantity and over there of the area vector. Okay, so you can say it like this. So it is associated with area vector. Okay, so this is the combination of two vector quantities, but they are not like the usual product or usual to have scalar product or the vector product. So this is like it is associated with area. Okay, and such kind of a quantity so is known as, which is of higher order, one order higher than the vector, so they are known as a tensor quantity. And as I've told you that moment of inertia is also a tensor quantity, just like the stress. Okay, so when we discuss the stress, the transformation of stresses, then we can apply the same rule to the transformation of the moment of inertia. Okay, so let's discuss this. So tensor is, the stress is a tensor quantity and stress is not a vector quantity. Okay, so the vectorial algebra is not applicable to the tensor quantities. You cannot apply the equilibrium condition to the stresses. You cannot apply equilibrium condition to the stresses. Okay, because you cannot aid them like vector. If the stress is acting in a center direction, in X direction, and then in a Y direction, and using head to tail rule, using the vectorial algebra, you just add them to get the result, and you cannot apply that to the stress quantity. Okay, you will have to develop some separate expression for the transformation of stresses. Now to derive an expression, जी, दोबारा बताएं.
tensor quantity.
टेंसर क्वांटिटी क्या?
सर क्या होता है?
टेंसर क्वांटिटी जो है एक वेक्टर क्वांटिटी. For a scalar quantity you require a magnitude only. For vector quantity you require magnitude and a sense only.
Yes.
And for a stress, which is a tensor quantity, you require magnitude, sense, and another requirement. For stress, that another requirement is the area on which it is acting. So stress is associated with the area on which it is acting. Like if you have tau x, y, so x is the area on which it is acting and y is the direction of this stress. So this x, this association with the area, this is associated with the area. So this association is another requirement. You cannot represent it with a single subscript. So this association is another requirement for this stress. Okay, so you will have to specify in which direction, on which area the stress is acting. Okay, so this area requirement is over and above the vector requirement. Okay, so that's why this is of higher order, and we say that this is a tensor quantity.
Yes, sir. For every tensor quantity, there is other quantity required are only the area.
No, other quantity required, like for the moment of inertia is like the depends upon the axis. So we say Ix, we say Iy, and we say Ixy. So Ixy is like you have x and then y. X is the xy is the plane, the Cartesian coordinate system. This is about simultaneously about both axes. Okay, this is not about one axis only. So moment of inertia, when we say Ix, so it means that it is Ixx. Okay, Iy mean Iyy, Ixy have left. It is similar to this one, but in those cases they are not, X and Y are not representing the area vector, they are representing the axis. So additional requirement. Okay, additional requirement. If you say that Ix is a vector, then in X direction, so this direction is important. Vector and direction. Okay, so Ix. So there is another requirement also. Okay, so it is not necessary that in all the cases area will be the area vector will be the requirement, but another requirement will also exist in the case of tensor quantity. Okay, so acha ji, so let's to derive an expression for stress transformation from xy frame of reference to x prime y prime frame of reference. Consider a general state of plane stress as shown in the figure. This is a general state of stress in of plane stress. So this is a two-dimensional state of plane stress, mean two-dimensional stress. So this is subjected to a sigma x, sigma y. This is same as this one. Okay, the sigma y, sigma y, and this is subjected to a shear equal to tau xy. This is tau xy. So since this is tau yx, but since we know that magnitude wise they are same, so I've written just as a tau xy. Okay, so this is tau xy, this is also tau xy, this is also tau xy. So when you just start derivation of something, so the quantity initially you take should be considered as a positive quantity. Okay, so I am starting with both sigma x and sigma y as tensile quantity. So in my derivation, the tension will be taken as positive, tensile stresses will be taken as positive. On x plane, the shear is producing a clockwise effect. On x plane, the shear is producing a clockwise effect, and on y plane, the stresses are producing a counterclockwise effect. So in my case, a shear on x plane, if it is producing a clockwise effect, will be considered as a positive number. Otherwise, it will be considered as a negative number. So for my sign convention, the normal stress will be positive and the shear stress producing clockwise will be positive. Okay. Now for theta, which is defining the Cartesian coordinate or the frame of reference in which you are defining, okay, let's suppose it is required to calculate on this pink plane, I require to calculate these stresses. So this plane is making a counterclockwise angle of theta with the x plane, or this x prime is perpendicular to the plane. This x prime is perpendicular to the plane, and this y prime is parallel to this plane. So this, if the angle between this is x plane, x or minus x, okay? So this is x plane and this is the required plane. So the angle between this is theta, so the angle between x and x prime will also be equal to theta. This angle will also be equal to theta, okay? So the theta which I am considering here in my derivation is a counterclockwise theta. Here you can see counterclockwise. So in my derivation, if theta appear, so that will be considered as a positive number. And if it is counterclockwise, then that will be considered as a negative number. So three sign convention for normal stress, for shear stress, and for theta. So I've discussed this, and you should remember the sign convention. Okay. Now it is required to calculate stresses on this plane. So this state of stress should be in equilibrium, because it is taken from a body and the body is in equilibrium. The body must be in equilibrium. So this point must be in equilibrium, and it is in equilibrium because this couple is balanced by this couple. This stress is balanced by this one, this is balanced by this one. Okay. Now, if this is in equilibrium, and if I am taking a part of this element, like this triangular part of this element, This is subjected to tau xy, this is to tau xy or tau yx. So this element must be in equilibrium because this plane is subjected to a shear tau x prime y prime, and this is subjected to sigma x prime. So this element must be in equilibrium. This must be in equilibrium. But since this is, I've taken it out and I have shown two stresses because this is a plane, and on this plane there must be a normal stress and there must be a shear stress acting on this plane. And it is my requirement to derive an expression for sigma x prime and tau x prime and y prime. This is my objective, and that will be, I will get an expression which will be in terms of theta, and I can use that expression for any theta. Okay, theta varying from 0 to 360 degree, I can use for any theta that expression. Okay, so since this is these quantities are the tensor quantity, are the stresses, so the equilibrium conditions are not applicable to this one. You cannot apply equilibrium condition that if you resolve some of the stresses into its component and then apply the equilibrium condition, you cannot do it like this because this is not a vector quantity, it's a tensor quantity. Then how to convert these tensor quantity into vector quantity? So you will have to multiply them with area, okay? So if you multiply these quantities with the respect to area, because the area of this element is higher, the area of this element is smaller, and the area of this element is smaller than this one. Okay, so they are dependent on each other, but you will have to use the respect to area of this element. So let's first talk about this one. This is the same triangle. So let's suppose the area of this element is dA. dA is the differential area of this inclined face. I'm sorry, not element of this inclined face. This is a line, but actually it is a face. Okay, it has dimension, like it has dimension. Let me draw those dimension. It has the other dimension like this. So this is a face, and similarly you have a bottom face and you have a top face. So if this incline, let's assume that this inclined face is dA, then from the from the trigonometry, that this area, this bottom area will be equal to dA sine theta, and this vertical area will be equal to dA cos theta. Okay, since this dimension is same, the thickness of all the element are same, so since this length, if this is dl, then this is dl sine theta and this is dl cos theta. So since all of them are multiplied with the same constant, so you can say if this is dA, then this is dA sine theta and this is dA cos theta. So these are the areas of elements. This is dA and this is dA sine theta. Now if you multiply these forces with the corresponding area, so you will get, this is sigma x dA, this is sigma x prime, this is tau x prime y prime dA, this is tau xy dA cos theta, sigma x dA cos theta, tau xy dA sine theta, and sigma y dA sine theta. So you have multiplied it with the corresponding area, okay, and you converted all these forces into its all these tensor quantities, all the stresses now to vector. Now these are vector, these are now sigma x prime dA is a vector. So all of them now vector. Now you can apply the vectorial algebra. Okay, you can apply the vectorial algebra. Now how to apply? So there are some forces are acting in xy direction and some forces are acting in x prime and y prime direction. So you will have to bring them into a common frame of reference. So to bring them to a common frame of reference, I'm resolving these xy component like this component, this component, this component, these four components along x prime and y prime direction. I'm resolving these forces. Okay, I'm resolving these two forces into their components along x prime and y prime direction. Okay, so let's first take this one. This is the force dA, sigma y dA sine theta. This one sigma y dA sine theta. So I know that the angle between this x is x prime. So if this one and this is along the y prime and this is along the x prime, so if this angle is theta, then this is also theta. Okay, so this is theta, then this is also theta. This is the sine component, this is the cos component because this is adjacent to the theta, and this is what, this is the sine component. Okay, so sigma y dA sine theta into cos theta, and sigma y dA sine theta into sine theta. So these are the two components. This component is along y prime axis and this component is along the x prime axis. Okay, similarly, now resolve this force into its component along x prime and y prime. So this is the force, this is theta, so this will be the cos component, so tau of xy dA sine theta into cos theta, and tau of xy dA sine square theta. And similarly, resolve this force into its component, okay, one along x prime, the other one along y prime, and similarly resolve this force into its component. Okay, these gray are the rectangular components of these forces. So I'll resolve these forces into its rectangular components along x prime and y prime directions. Now I'm applying the equilibrium. Since there are forces, I can apply the equilibrium condition. Okay, so the equilibrium condition here, I'm applying that some of the forces in x direction, x prime direction should be equal to 0. So some of the forces in this direction should be equal to 0. When I'm taking forces in this direction, the positive x prime direction is positive. So this force, sigma x prime dA, okay, minus this force, sigma y dA sine square theta, plus tau of dA sine theta cos theta, minus this sigma x dA cos square theta, or plus this tau of dA cos theta sine theta is equal to 0. So if you can see dA is everywhere, you can take it out and it will become 0, and just keep sigma x on the left side of this is equal to sine and bring all the other quantities to the right side, so you will get this expression A. Okay, this expression A, if you just look to the right hand side, sigma x is known to you. The right hand side is in the xy frame of reference, and the left hand side is in the x prime y prime frame of reference. So this is sigma x is known to you, sigma y is known to you, tau xy is known to you, because they are the known. The state of stress is known to you in the xy plane. The state of stress is known to you. So if you plug in any value of theta in this expression, you will get what? You will get this, the stresses in the prime direction, the x prime, the normal stress in the x prime direction. Okay. Now, if you apply equilibrium condition along the y prime axis and a summation of f y prime is equal to 0, and taking all forces in this direction is equal to as a positive quantity. So this is a negative force, tau x prime y prime dA. This is again a negative force, sigma y dA sine theta cos theta. This is again a negative force, minus tau xy dA sine square theta. This is again, this is a positive force, sigma x dA sine theta cos theta, and this is also a positive force, tau x y dA cos square theta is equal to 0. So if you simplify this one, so tau x prime y prime is equal to sigma x minus sigma y sine theta cos theta plus tau x y cos square theta minus sine square theta. Okay, cos square theta minus sine square theta. So you got these two expressions. One is giving you the normal stress at some inclination, and the other one is giving you the shear stress at that on that inclined plane. Okay, and there are two stress components in a plane. There are two stress components. One is normal and one is shear. And for a plane body, okay, if the z direction is stress free, then you have these two stress components, and you can calculate with this one. Okay, now to have a complete state of stress at this point in the x prime y prime direction. Okay, if you want to complete the state of stress, so you need to know the stresses on a plane perpendicular to this desired plane. Like you need a stresses on this plane, which is, if this is x prime plane, then this must be the y prime plane. So you need to know the stresses on the y prime plane. Now, the y prime plane, this plane is making which angle with the y prime plane is making an angle of theta plus 90 with the x1. Y prime kitna angle bana raha hai? So it is making, this is a y prime plane. Let me draw the y prime plane. This is a y prime plane. This is a y prime plane, and this is the normal of this. So this angle from here up to here, this angle is, since this is theta and this is 90, so this is theta plus 90. Theta plus 90. Okay. So I can use the same equation which I derived for what I derived for the sigma x. So I can use the same equation to get an expression for sigma y. So let's, sigma y is what? If I just use the angle of theta plus 90, theta will give me sigma x, but I'm using theta plus 90 in the same expression, so that will give me sigma y. So sigma y, sigma x cos square theta plus 90, I'm replacing theta with theta plus 90. So sigma y sine square theta plus 90 and this one. Now cos theta plus 90 is minus sine theta, and sine theta plus 90 is cos theta. So just use this expression, so you will get an expression of sigma y is equal to sigma x cos square theta plus sigma y sine square theta plus 2 tau xy sine theta cos theta. So I got the three expression now. One is for sigma x, the other one for sigma x prime, other one for sigma y prime, and other one for tau x prime y prime. So I got expression for this one. So I just rotated the element. Okay, and rotated mean you just rotated the element to get stresses in some other orientation. Okay, in some other orientation. So you can calculate sigma x prime, tau x prime y prime, and sigma y prime using equations A, B, C. Okay, using these expression A, B, C. So here you can see that this is not just the vector thing. Like if vectors are in certain direction are known to you, then how to get vectors in the other direction. So it is not like that. Okay, so it is something, a different kind of a thing. So these are the equations which are related to the tensor quantities. These are used for the transformation of the tensor quantities. Okay, now I can convert this equation ABC using the half angle formula. The formula that's cos square theta is equal to 1 plus cos 2 theta by 2, sine square theta is 1 minus cos 2 theta by 2. Okay, I can convert this and plug in the value. So finally I will get sigma x prime is equal to this one, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta minus tau xy sine 2 theta, and similar for other equation. This is when I converted equation A, equation B, equation C, or using the half angle formula. Why I need this? Why I converted this into this formulation? So there are two reasons. One reason is they are easy to remember. Okay, these equations are easy to remember. They are also related to when we'll discuss the Mohr circle formulation. So they are also we'll get an expression for the Mohr circle. So they are easy to derive from this from these expressions. Okay, this is one thing. The other thing is that at the time when Mohr developed the graphical solution for the stress transformation, so at that time, so this formulation was developed before the Mohr this transformation equation. So at that time there was no calculator. So just to get this, even to get the trigonometric relation, they were using the table. Okay, and just to get the square, so just you can imagine, if you want to just take a square of 123.6 in multiply by 123.6, so you will have to multiply then how much time is required for that one. So they wanted to avoid this kind of a square. Okay, so they converted this, and there is no square number in these equations. So the main objective at that times was this one. Okay, and then later on more circle, develop this more circle, and what is the relation between these equation and the more circle. We'll discuss that in our coming class. Okay, so these are the three equations. Now we'll be dealing with these three equations. Okay, we'll not deal with this A, B, C. We'll be dealing with these three equations. Okay, so let's have an example, a very quick and short example. Okay, for the given state of stress, this is the given state of stress. Calculate stress components on a clockwise angle of 30 degree on a,
Excuse me, sir.
yes.
Sir, is there any assumption for these equations?
No, there is no assumption for this equation.
Okay, sir.
With regard to the formulation, the getting of the equation for sigma x and sigma y, those assumptions are applicable. And one assumption is that the bodies should be elastic. Obviously, it should be. We are considering the since the formula which is used to calculate the sigma x, sigma y to xy, they are based on the elastic body. So this transformation is also based on the elastic body. So it's a good you ask this question. So there is no such independent assumption for this one, but the only assumption which should be that the body is elastic, isotropic, homogeneous. Okay, so these are the cases.
Okay, sir. Thank you, sir.
I may not be the requirement, but elastic and isotropy is the requirement. Okay, elastic and isotropy is the requirement. Okay, so now here, this is the state of stress that for the given state of stress, he is saying that you calculate stresses at a clockwise angle with the x-plane. So this is the x-plane. You can show it here also, but I'm showing it just to show it's normal in this direction. So this is the required plane which is making a clockwise angle. If you draw it like this, so it will make a counterclockwise angle. So this is making a clockwise angle of 30 degrees. Okay, so and this is normal to this plane. So if this angle is 30 degrees, then this must be 30 degrees. And from x to x prime, x is the angle should also be 30 degrees. Okay, so it is required to calculate stresses on this plane, and this angle is a clockwise angle. So according to our sign convention, sigma x is plus 10 because this is tensile. Sigma y is minus 15 because this is compression. Tau xy is minus 12. Why this is minus 12? You will have to look tau xy. You will have to look to the x plane. Okay. So on the x plane, the stress is producing a counterclockwise effect. So that's why this is given the negative sign. And it is important. If you just plug in a positive value, everything is gone. You will get a wrong result. Okay. So you must have to plug in a positive value. I'm sorry, a negative value correspondingly. Okay, if it is counterclockwise, it is producing a counterclockwise effect. This is a clockwise angle, and we say that clockwise angle, the sign convention for shear and theta are opposite. Shear clockwise is taken positive, but theta counterclockwise is taken as positive. Since this is clockwise, so it is taken as a negative. This is according to the sign convention. Okay, so now plug in the value. So sigma x prime is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta. So just plug in the value. So 10 plus minus 15 by 2 plus 10 minus 15 by 2 cos of 2 theta. So theta is minus 30. So 2 theta is minus 60. Minus is of the formula, and this tau xy is minus 12 sine of minus 60. So if you simplify this one, you will get minus 6.64. So on this plane, the normal stress is a compressive stress equal to minus 6.64 MPa. Similarly, tau xy, the shear stress on this inclined plane, is equal to sigma x minus sigma y by 2 sine of 2 theta plus tau xy cos 2 theta. So plug in the value 10 minus 15 by 2 sine minus 60 plus minus 12 cos minus 60. So it is resulting in minus 16.82, meaning that it is negative. It is producing a counterclockwise effect. Okay. So this will complete our calculation. These are the stress components required on the plane. But if you want to complete the whole state of stress, if you want to show the whole state of stress, you need only this plane is same as this plane. So this plane, you have a compressive stress and you have a counterclockwise shear stress. So now your calculation is complete. But to complete the state of stress, you will have to also calculate this 1.64, though it is not required in this problem, but I want to complete the state of stress, so that's why I'm calculating sigma y prime also. So sigma y prime, when I calculated it is 1.64, so this is a tensile stress. So this is the complete state of stress in this orientation. This is the orientation, so this is the complete state of stress. Okay, so you now convert it, this state of stress to this state of stress. You rotated this out. Here you can see that here the shear is plus 12, but here the shear is 16.92, obviously higher than this one. There will be another plane at which the stress will be even higher than this value. And how to get that we'll discuss in our coming few slides. Okay, so this is, you converted to show this kind of a state of stress and to show this result. This is important. Calculation, plugging value in a certain equation and getting the answer, this is not the objective. Objective is that you should know that in which direction the stresses are produced. Okay, if you show it in a wrong way, then everything is gone. Okay, you will have to show it in a particular way. So you must be able to rotate a state of stress and to show the state of stress like this. ठीक है ना, आपको ये इस तरह शो करना, so this is important for you. Okay,
Sir,
जी,
sir, I'm still confused about the angle. Sir, 30 degrees पर आपने दे दिया सर, या हमने स्ट्रेस लगा दूसरे के वजह से हमने ये बन गया सर, ये किसके वजह से
किस लिए दिया गया ये 30 का एंगल?
जी सर,
नहीं, अभी हम इस चीज को डिस्कस नहीं कर रहे हैं कि किस लिए दिया गया. हमसे पूछा गया कि the state of stress in XY plane is given to you. Okay, you know the stress is on X and Y plane, and he is asking you to calculate the stresses on this inclined plane. This is the question. This is an academic question. Why we are calculating this one? This is something, this could be, like as I discussed, this could be a problem. This could be the weaker plane. Okay, this could be the weaker plane. Okay, मतलब हमें बस बता दिया कि इस आप इस एंगल पर जो है वो कैलकुलेट कर लो. ठीक है ना, हम तो इस चीज में जो है वो हर एक चीज को उसके साथ रिलेट नहीं कर. आप inclined direction में stresses are required, so he's asking you to calculate stresses in that inclined direction.
सर मतलब ये एक पॉइंट है और हमने इसे रोटेट किया.
बिल्कुल, ये एक ही पॉइंट है और उस पॉइंट पे आपने इस एलिमेंट को रोटेट किया. ये this is not another point, this is the same point, बिल्कुल exactly same point है, but you rotated the element and you got stresses in some inclined orientation at the same point. This is important. This is not like at the other point. This is at the same point but in different direction.
Yes,
when
clear.
in direction, so the values of the stresses are changed, and this is the transformation.
Yes.
Not transformation from one, as I've already told you, this is not transformation from one point to the other point. This is transformation from one orientation to the other orientation. Okay?
Yes, sir. Thank you. Sir, एक और क्वेश्चन है सर.
जी.
सर ये जो होता है था x y. No sir, sorry, था x x. सर इसका मतलब होता है कि टार्क एंड x प्लेन इन डायरेक्शन.
नहीं, tau x नहीं होता.
सर स्ट्रेस
Normal stress have the same subscript, but the shear will always different subscript. Okay, shear.
सर उसके सर जब ज्योमेट्रिक प्रॉपर्टी सर उसमें ये x x की जो कंपोनेंट है सर उसकी डायरेक्शन सर इसे गोल शक्ल में आपने दे दी थी सर. तो जब सर ये एक जब लगता है सर फिर किस तरह की डायरेक्शन पर गोल आता है?
नहीं, this x is the first one is showing you the plane on which the stress is acting, and the second subscript is showing you the direction on which in which the stress is acting. One is the plane direction, like this is acting on x plane in y direction. So this is what this line, which is you can see this is a line, but actually this is a plane. So this is x plane. Okay.
Yes.
So this is the stress acting on x plane, but the you see the direction is in y. So this is in this name, tau xy. It is acting on x plane, but acting in y direction.
Yes, sir. Sir, तो ये तो डायरेक्शन सर इसकी वही की तरफ हो गया ना?
हाँ? क्या हुआ?
डायरेक्शन वही की तरफ हो गया ना, डायरेक्शन वही की तरफ हो गया।
y की तरफ डायरेक्शन, y की इसका डायरेक्शन है।
और सर आपने
सर
सर तो हम ज्योमेट्री क्लास तो सर पढ़े थे ना, पढ़ रहे थे सर, तो हम ज्योमेट्री क्लास तो पढ़ रहे थे सर, तो उसमें आपने एक स्ट्रेस दिखाया है और उसकी डायरेक्शन पर कुछ और तरफ है, और उसकी जो एक्स एक्स।
आप कहाँ की बात कर रहे हैं? मुझे आपकी बात समझ नहीं आ रही
सर।
जी
सर इससे कहें कि अगर ये किसी दोस्त के साथ बैठा है तो जब सवाल पूछे तो उसको कहे कि वो बंद किया करो, उसकी आवाज दोबारा आती है सर।
हाँ ना, वो मतलब उसमें आपकी आवाज भी साफ नहीं आ रही है और मैं आपके क्वेश्चन को समझ नहीं रहा।
सर मैं लास्ट क्वेश्चन सर आप लेक्चर स्टार्ट करें।
Okay, so this was how to calculate stresses at some inclination. Okay, now coming to some other topics. Now, principal stress plane. Okay, so this is like a plane. This is like a plane. Okay, so when you are rotating this plane, so there are two actually planes who have some particular properties, and those planes are known as principal plane. And what are those principal plane? What are the properties? So the two orthogonal planes where the stress is maximum at one plane and minimum at the other. Two orthogonal plane, there are two orthogonal plane. Orthogonal means they are perpendicular to each other. Okay, two orthogonal plane. On one plane the stress is maximum, and on the other plane the stress is minimum. Okay, and the stresses are known as principal stresses denoted by sigma 1. The stresses acting on those principal plane are known as principal stresses, and they are denoted by sigma 1 and sigma 2. Sometimes they are denoted by sigma max and sigma min, sigma maximum and sigma minimum, but usually they are represented with sigma 1 and sigma 2. Okay, so how to get, this is the problem, how to get the maximum stress. You have an expression like this expression, that this expression is giving you the normal stress at any orientation. Then there will be an orientation of at a certain theta where the stresses will be maximum. And how to get that? How to get that? So we have the maxima and minima principle. You take the derivative of the function. Okay, so you have the sigma is equal to this one. So you take d sigma by d theta because you want to know the particular theta जिस पर वो plane lie कर रहा है. So d theta by d by d theta of this one, and just if you just take the derivative of this is a constant. So because you are taking derivative with respect to theta, so this is constant, so 0. This time cos 2 theta, so the derivative of cos 2 theta is minus 2 sin 2 theta. Minus times y, the derivative of sin 2 theta is 2 cos 2 theta. So this is equal to, make it equal to 0. This is the way. Okay, you take the derivative and then make it equal to 0. And then if you simplify this one, so you will get tangent of 2 theta, and using now the subscript n is equal to minus 2 tau xy divided by sigma x minus sigma y by 2. So this equation A will give me a particular theta or a particular plane. Okay, this equation will give me a particular plane, and at that plane the stresses will be principal stresses, either maximum or minimum. Okay, either maximum or minimum. This is the usual way of how we get the maximum value of a certain function. So I've used that mathematical procedure just to get the maximum value of that. So this will give you this will give me a value of theta, and theta defines the plane. ठीक है ना, वो theta मुझे मिल जाएगा, and that defines the plane. Okay, and this will give me a theta, and if I plug in that value, bake in the expression of sigma, so that will give me a certain value of stress, and that stress will be the principal stress. Now, to get an expression for the principal stress, this is one way to just get the value of theta and then plug in, and then plug in the expression and get the value of stress. But to get an expression for theta, so this I've represented this equation with the help of these two diagrams. Here you can see this is minus tau xy, this is sigma xy, sigma 2, and this is 2 theta n. So here you can see that this is tangent of 2 theta n is equal to minus tau xy divided by this. Okay, this triangle is representing this equation. This triangle is also representing this equation. Here, this is negative, but this is positive. And here I've converted this positive to negative, because this negative sign can be with this tau xy, and this negative sign can be with this minus sigma x by sigma y by 2. So here I have written it with this one, and this will also, since tangent of 2 theta n is this divided by this, so this will also give me this one. So this triangle is also giving me this value, and this triangle is also giving me this value. So these are two triangles which are corresponding to these equations. Now, for these two triangles, if I calculate sine of theta, so for the first triangle, so the sine of 2 theta is this divided by, I've calculated this according to the Pythagoras theorem. This is a right angle triangle, so this square plus this square under the root will give me this one. This hypotenuse of this, or this inclined line of this one, inclined length of this one. Okay, so sine theta for this is this divided by this. Okay, minus tau xy divided by this, and for this is minus tau xy by this, and this is plus tau xy by this, so plus minus this one. Okay, so this is plus minus this one. Okay, plus is for one triangle and the minus is for other triangle. And similarly, cos theta is this divided by this and this divided by this, so plus minus this. Okay, plus minus this. So I got expression for sine 2 theta and I got expression for cos 2 theta. Now I'll plug in these values, the sine theta and the cos theta, in the expression. This is expression for the stress transform. This is stress transformation equation, sigma x plus sigma y by 2 plus this. Now if I plug in theta n, so it will give me what? It will give me 1 and 2. The principal stress is 1 and 2. It will give me those values. Now plug in the value of sine 2 theta n and cos 2 theta n and sine 2 theta n from these two triangles. Okay? From these two expressions. So plug in, so plus minus this, plus tau xy plus minus this. Just this is divided by this, so take it out common. So this into this square plus tau xy into tau xy square. Okay, so you will get this one. So here you can see that this is in under root and this is without under root. So this will then become under root. जो है वो इसका आ जाएगा. So this is what, I'm sorry, ये मैं कहाँ पर आ गया? आगे चला गया. So this is sigma x plus sigma y by 2. Plugging the value, simplify this one, so I'll get this expression. Sigma x plus sigma y by 2 plus minus sigma x minus sigma y by 2 square plus tau xy square. Okay, so this equation 2, one is plus and the other one is minus. So sigma 1 mean plus if you add these two quantity, and sigma 2 mean if you subtract, if you use a negative sign of this equation. So you will get two values. Okay, you will get two values. So in this case, I'm going back. You got an expression for the principal plane. This will give you the principal plane, and you got expression for the principal stresses. Here on the right hand side, you can see that there is no theta. just sigma x, sigma y, and tau x by plugging on the right hand side, so you will get the principal stresses. And the principal stresses by definition are the maximum and minimum stresses, the two extremes. In all other orientation, the stresses will be in between sigma 1 and sigma 2. There will be no stress greater than sigma 1, and there will be no stress lesser than sigma 2. When I'm using the maximum and minimum, so on the positive side it is maximum, like -2 is maximum and -20 is minimum. -2 is maximum because this is more near to the positive side. So this is algebraic maximum and minimum. Okay. So if you have two stresses, -10, -20, so -10 will be sigma 1 and -20 will be sigma 2. And if you have +10 and +20, then +20 will be sigma 1 and +10 will be sigma 2. Okay, so this is algebraic. On positive side, the higher value will be taken as sigma 1 and the next will be taken as sigma 2. So you will get the two values. So this is the principal plane. You have sigma 1, you have sigma 2. Sigma 1 is this plus this. Sigma 2 is this plus sigma this. And this is theta n. This theta n is calculated from equation number 1. Okay. Now, you located the principal plane and you calculated the normal stresses on the principal plane. You derived an expression for those one. Now, let's calculate shearing stress on principal plane. What will be the value of shear on principal plane? So let me call that as a tau theta n. So I have expression for sigma x minus sigma y by 2. This is expression for shear at any inclined plane. So at theta n, so this is equal to this one. So plug in the value of sine 2 theta n. This is basically sine 2 theta n and cos 2 theta n. Plug in the value. Okay, so you will get finally a 0. Okay, this will cancel with this one. So you will get a 0 value. So it means that on principal plane, the shear stress is 0. Always this will be the case. I'm using the general expression. So the general expression is giving me the 0 value. So always on the principal plane, the shear stress there, here you can see that there is no shear component here. There is no shear component. Okay. So on the principal plane, the shear stress is 0. And this is the identity of the principal plane. If a state of stress is given to you and you see that there is no shear stress acting at that point, in that orientation, so you can say that this is the principal stress. This is the principal plane, these are the principal stresses. So this is the identity of the principal plane, that on the principal plane, the shear will be 0. Okay. This is the identity of the principal plane. So let me repeat this using the maxima and minima principle. I derived an expression for the orientation of the principal plane. Then I plug in the value of the principal plane, the theta n value, and I got expression for sigma 1 and sigma 2, the principal stresses. And then I calculated on the principal plane, I calculated that the shear stress on the principal plane is equal to 0. Okay. Now coming to the next. The maximum and minimum shearing stress plane. The maximum and minimum shearing stress plane. We talk about the normal stresses. The principal planes are for the normal stresses. Then you must know what will be the plane at which the shearing stress will be maximum. How to look at that plane and how to get an expression for the maximum and minimum shearing stress. So the two orthogonal planes are, well, luckily these are also orthogonal. Two orthogonal planes. The principal plane are also orthogonal. Okay. So the two orthogonal planes where the shearing stress is maximum at one location and minimum at the other. These stresses are known as in plane. There is a word in plane. We'll talk about this in plane in the last of this lecture. In plane maximum, minimum shearing stress denoted by tau maximum and tau minimum. Okay, the maximum is denoted by tau maximum and the minimum is denoted by tau minimum. Now to derive an expression for maximum minimum shear stress, take the derivative of shear stress transformation equation equal to 0 and determine the value of theta, just like we did in the case of principal stresses. But here I am taking the derivative of the equation 2 or the equivalent to equation 2. Okay, so this is the shear stress equation. Take the derivative and make it equal to 0 and get an expression. So this will give you tangent of 2 theta s. Okay, tangent of 2 theta s The previous one was tangent of 2 theta n, and that was like minus tau xy divided by this, and here it is sigma x minus sigma y by 2 divided by tau xy. Okay, so this is the expression of the maximum or minimum shearing stress plane. Equation 3 gives the orientation of this plane. There are two possible solutions of equation 2. Just the previous case, maybe we did it for the normal case. So this equation is satisfied by this. Since this is a positive number on the right hand side, you have this positive, this positive. So here you have both positive and here you have both negative. Because if taking both as negative, so both negative can result also in a positive ratio. Okay, of the two. This divided by this will also result in this one. So both triangles satisfy this equation. So cos of 2 theta n is equal to this divided by this, and sine of 2 theta n, and plus minus, here plus and here minus, and sine of 2 theta n is this divided by this. Okay, so just you got this and plug in the shear equation, the shear transformation equation. So this is the shear transformation equation. Plug in the value of sine 2 theta s and cos 2 theta s, simplify, so you will get this expression. So this expression, the plus sign corresponds to maximum shear stress and the negative sign corresponds to the minimum shear stress. So one thing is clear from this expression, that the maximum and minimum stresses are same. But one is positive, other one is negative. A is against the principal stresses. Principal stresses are not necessarily same. जरूरी नहीं है कि वो same हो, but the shear stresses are always same. If one is plus, the other one is minus. Okay, since on the two orthogonal plane they are orthogonal stresses, on the two orthogonal plane the stresses must be same. Again, if you have a stress of 100 on this plane, there must be a stress of 100 on this plane. So since the maximum minimum are orthogonal, so they must be same in magnitude. This is equilibrium requirement. Okay, so I got expression for this one. So I got expression for the theta, and I got expression for maximum. Now, as we calculated that on the principal plane, the shear is 0. Now let's calculate the normal on the maximum shear stress plane. Okay, the normal on the maximum shear stress plane. So this is the expression. So this is the normal on the maximum shear stress plane. This is plug in the theta s, so cos 2 theta s, sin 2 theta s, plug in the value. So you will get finally a number sigma x plus sigma y by 2, not equal to 0, and a same number, not a plus minus number. So it means one thing, that on the maximum minimum shear plane, the normal is not 0, is against the principal plane. Principal plane par shear 0 tha. But here on the maximum minimum shearing stress plane, the normal component is not 0. Normal 0 nahi hai. Normal is having some value. Okay, and that value is sigma x plus sigma y by 2. This is one thing. And on both minimum and maximum plane, the normal component are same. Since you got a same value for both plus and minus, you got the same value sigma s. So on this plane, this is sigma s. On this plane, this is also sigma s. Again, sigma s means this is the normal component on the shear plane. S is for shear. Okay, so this is what this is. Once again, the identity of the maximum shear stress plane. If you see a plane, a state of stress, we are both normal on both x and y plane, the x prime, y prime, or x or y plane, the normal component are same. Then you can say that this is the maximum plane. As per जो stress होगा वही maximum होगा. Okay ना? वही जो है वो maximum होगा. ठीक है? That will be the maximum stress. So this is the identity. Just like the identity of the principal plane is that the shear is 0. Identity of the maximum shear is that on the both vertical plane, the normal will be same. Same in magnitude and sense both. Okay, दोनों तरीके से जो है वो same होने चाहिए. ठीक है? So this is, we got, let me summarize, we got an expression for the maximum shear stress plane. we got expression for the maximum minimum shear stresses, and we got expression for the normal stress on the maximum shear stress plane. Okay, so this is the complete state of stress for the maximum shear. Okay, complete state of stress for the maximum shear, and this is complete state of stress for the normal component. Okay, complete state of stress because the shear is zero here. Okay, now relation between principal stress and maximum shear stress. Is there any relation between the two or not? One thing is that what is the relation between, is there any relation between the plane? So we know that tangent of 2 theta n is equal to this one and tangent of 2 theta s is equal to this one. Okay. Now equation A and B shows slope of lines or planes lying at double angle of principal plane and the maximum shear stress plane. This line, this is what, this is a line, this is not the plane, this is at a plane is here. Plane is at theta n. And this is also, this is 2 theta s, this line is 2 theta s, it is some, the actual plane is here. This is the slope of a line. So this equation is giving you slope of lines playing like a double angle, there double angle. A tangent of any angle is the slope of that line. So here 2 theta n. So this is the slope of a line whose angle is 2 theta n. Okay. So these are showing the slope. Now when you multiply this with this one, you get what? Minus 1. And this is slope, this is slope. So this is not the slope of the principal plane, this is the slope of the double of the principal plane. And this one is the slope of double of the maximum shear stress plane. Not the same line, but at a double angle. Okay, so when you just, this is like M1 and this is M2, product of two slope, if it is equal to 0, then what does it mean? इसका क्या मतलब है? बताएं?
It means parallel.
Parallel.
They are parallel to each other. Is it okay? कोई और बताए? If you have two lines and their slope, if you multiply the slope of the two lines and if it result in -1, so what does it mean?
They are perpendicular.
They are perpendicular. Good. They are perpendicular to each other. ठीक है ना? ये एक दूसरे के perpendicular जो है वो होंगे. ठीक है ना? So tangent of 2 theta n multiplied by tangent of 2 theta s is equal to -1. So it means that the angle between 2 theta n and 2 theta s is 90. Like 2 theta n minus 2 theta s, if you take absolute, it should be equal to 90. ये मुझे इस equation से मिला. Okay, and if I take it out theta common, so theta n minus theta s is equal to 45. Or means that the angle between the principal plane and the maximum shear stress plane will always be equal to 45 degree. दोनों के बीच में angle कितना होगा? 45 degree का होगा. दोनों plane, both planes will make an angle of 45 degree with each other. Okay, so this is one relation. This is relation between the planes. Okay, they are not independent of each other. Their orientation is one dependent on each other. Okay, now if you know the principal plane, then the maximum shear stress plane will be at an angle of 45 degree. Okay, or minus 45 degree. Okay, now thus the angle between the principal plane and the minimum stress plane is always 45. Maximum shear stress may be written in terms of the principal plane. Okay, now if you just take, you have expression of sigma 1 and you have the expression of sigma 2. If you subtract it and take the absolute of this, so this is sigma 1 and this is sigma 2. Okay, sigma 1 minus sigma 2. Okay, so what you will get this as, if you subtract it, so this will cancel with this one and it will result in 2 times of this. This is what this expression. ये क्या चीज है? This is tau maximum. ये क्या है? Expression is tau maximum. ये पूरा sigma 1 है, but this expression is tau maximum. Okay, so if you, this will cancel with this one, but this will become 2 times. So 2 times of tau maximum. So if you take difference of sigma 1 minus sigma 2, you will get 2 tau maximum. So tau maximum is sigma 1 minus sigma 2 by 2. Yani there is a relation between the stresses also. Okay, so if the principal stresses are known to you, then tau maximum you can easily calculate using this expression. वैसे तो आपके पास जो है वो tau maximum का expression, let me go to the previous slide. Tau maximum का expression ये है. But if you have principal stresses, so this will sigma 1 minus sigma 2 by 2 square plus, since at the principal axis this is 0, so this will 0 square will cancel with this one, so you will get sigma 1 minus sigma 2 by 2. Sigma 1 minus sigma 2 by 2. Okay, so this is an expression for tau maximum. Tau maximum, and this is a relation between the principal stresses and the maximum shear stresses. Now let's do this example. फिर हम जो है वो एक ब्रेक की तरफ जो है वो जाएंगे, ठीक है? For the state of stress, calculate principal stress and maximum minimum shearing stress. This is a state of stress जो हम पहले discuss कर चुके हैं. We discussed this this state of stress. So this is sigma x is plus 10, sigma y is minus 15, and tau xy is minus 12, and it is required to calculate principal stresses and maximum and minimum shear stresses. So principal stresses, let's locate also to calculate, so it's very easy. Okay, but let's locate the plane also. So theta n is half tangent inverse of this is equal to half tangent inverse of this, so this results in plus 21.9 degree. So the principal plane is making an angle of, since this is a plus 21, so it is making a counterclockwise angle with the x plane. X plane के साथ counterclockwise angle 21.9 degree का जो है वो बना है. ठीक है, यहाँ पर आप देख सकते हैं. ठीक है ना, कि ये हमारा state of stress है. So when I rotate this with a counterclockwise angle of 21.9 degree, so I'll get these principal stresses. This is expression for the principal stresses. I derived this. You need just to plug in the value of sigma x and sigma y and tau xy in this expression. So you will get 10 minus 15 divided by 2 plus minus this. So you will get minus 2.5 plus minus 17.3. So sigma 1 is 14.8 and sigma 2 is minus 19.8. Okay. So you got these two values. Now, this angle is associated with this one or with this one. This is not known to us. If I'm rotating the element with a 21.9 degrees, so whether I'm getting on this plane I'm getting minus 19.8 or on this plane I'm getting 14.8, this I will have to check. Okay, so to determine whether theta n of 29 coincides with sigma 1 or sigma 2, किसके साथ coincide करा? Because it can coincide with any one of them. It can coincide with any one of them. So how can I get this value? So put the value of theta n in the transformation equation. This is the transformation equation. Put the value of theta n in this expression. This is 21.9 is 2 times is 43.8, and plug in the value, so you will get either 14.8 or minus 19.8. So here I get 14.8, so it means that 21.9 is associated with what? With the maximum stress of sigma 1. This is maximum and this is minimum. So this is 14.8. So here you must have to, if you are showing this as minus 19.8, so you are wrong. You will have to show it, you will have to check it whether it coincides with positive sigma 1 or sigma 2. So it is, we confirm that it is coincide with sigma 1. So this is 14.8. So this is the principal state of stress. Now you know the orientation, कि किस direction में stresses है, ठीक है ना? And you know the values also. Okay, you know the values also. Okay, there the maximum value is 14.8. All other values will be greater less than this one, and this is the minimum value of minus 19.8, and all other stress value will be greater than this one. Greater mean algebraic greater. ठीक है ना? Now to calculate the principal, to locate the principal plane, so we have theta s is equal to half tangent inverse of this, so we got minus 23.1. And the tau maximum minimum is expression this one, so this is plus minus 17.3. So tau maximum is plus 17.3 and tau minimum is minus 17.3. Now once again, this angle minus 23.1 is associated with this one, or it is associated with this one. So you will have to put the value in the transformation equation. So this is the transformation equation, and this is transformation equation. So just plug in the value, so you get that it is coinciding with the negative, with the minimum shear. So when you just rotate the element by 23.1 degree, rotate it by 23.1 degree, but this is negative, mean you will have to rotate it clockwise. Okay, clockwise isko rotate kar le. Okay, when you rotate it, so on this plane you will have to show the minimum stress 17.3. so minimum mean negative, so negative mean counterclockwise. Here you can see this, and this is counterclockwise. So you will have to show it as a counterclockwise. Okay. Now the normal stress at the maximum minimum shear stress plane. So we have expression sigma x is equal to sigma x plus sigma y by 2. So here I get minus 2.5 ampere. So this is minus 2.5 ampere. This is minus 2.5 ampere. So this is the state of stress, the complete state of stress corresponding to the maximum shear stresses. You have 17.3 is the maximum value of the shear stress. इससे ज़्यादा नहीं हो सकती. All other shear value will be less than this one. ठीक है ना? इससे कम जो है वो होंगी, इससे ज़्यादा जो है वो कोई नहीं हो सकता. And one thing more, that the angle between the principal plane, we know that the angle between principal and the maximum shear stress plane is, you subtract 21.9 was the principal and minus 23.1. So this is resulting in a 45 degree angle. Okay. और principal plane ऐसे था ना, इधर था और ये इधर है. So the angle between the maximum shear stress plane and the principal plane is always 45 degree. ठीक है ना? Let me show it on the actual plane. So this is what, this is principal plane, okay, and this is the minimum, the maximum shear stress plane. Principal plane, the maximum shear stress plane, and the angle between the two is 45 degree. Okay, 45 degree. And it must be, it is always, it should always be 45 degree. Now let's discuss this stress invariant, and then we'll discuss summary, and then one example most probably, क्योंकि हमने 10:30 बजे इसको conclude जो है वो करना होगा. आपका आज quiz भी है, ठीक है? Let's discuss the stress invariant, and then we'll move further. There are some properties which remain constant during stress transformation from one plane to the other. These constants are called stress invariant. These invariants are used as checked in the stress transformation. The two important stress invariants are, जो दो important stress invariants हैं, वो क्या हैं? Some of the stresses will be constant. What does it mean? That sigma x plus sigma y must equal to sigma x prime plus sigma y prime plus sigma n plus sigma. Just plane per b, when you calculate stresses on any other plane, so their sum must be constant, must be same. Okay, just like, let me show that in example 2.1 and 2.2, we calculated the original one, sigma x plus sigma y was 10 plus minus 15 is equal to minus 5. When we calculated on inclined plane at an angle of 30, so minus 19.24 or plus 4.24, so it is minus 5. When we calculated the normal stresses, so 14.8 plus 1 minus 19.8 is equal to minus 5. Even for the maximum shear plane, let me show you, I'm sorry. On the maximum shear stress plane, you have minus 2.5, minus 2.5. The sum is what? Minus 5. Okay. So all the cases, so you can use them as a check. When you calculate sigma x prime and sigma y prime, just sum them up and sum the original sigma x and sigma y. So if they are same, then you can say your calculation is okay as far as the normal stress is concerned. Okay. Now the next stress invariant is that sigma x minus sigma y by 2 square plus tau x y square. ये क्या चीज है? This is basically if you take the under root of this, so this is tau maximum. इसका under root ले ले तो वो tau maximum. Yani it means that the shear stress, the maximum shear stress, if you calculate from any orientation, that will give you the same result. Okay, so if you use the xy plane, if you use the x prime y prime plane, or if you use the principal plane, and on the principal plane, since you have only this component, the shear is 0, so there is no shear, and it must be equal to the tau maximum square. Okay, so this is another stress invariant. So I'm calculating this for the xy, so I'm getting 300.25. When I calculated it from x prime and y prime, I got the 300.25. When I calculate sigma 1 minus sigma 2 by 2 square, so I got 300.25, and this is the tau maximum. So I've calculated the tau maximum also. Previous slide पे मैं जा रहा हूँ. This is the tau maximum. So if I take square of this one, I'll get the same value. ठीक है, 300.25. ठीक है ना? आप जरा ले लें उसका, तो वो आपको जो है वो सेम रिजल्ट देगा. So this is stress invariant. These stress invariants are used as a check in the stress transformation. आप अपनी कैलकुलेशन को इससे चेक कर सकते हैं. ठीक है ना? आप कैलकुलेट कर लें. When you just do calculation, just apply these checks. ठीक है ना? ओरिजिनल के लिए आप ये कैलकुलेट कर लें, और जो आपने कैलकुलेट किया उसके लिए ये चीज कैलकुलेट कर लें. ठीक है? So वो अगर ठीक आ रहा है, दोनों एक जैसे आ रहा है, so it means your calculation is okay. So these are the stress invariant. यहाँ पर हम एक ब्रेक लेते हैं. ब्रेक के बाद जो है वो इंशाल्लाह इस चीज को समराइज करेंगे, और आई डोंट थिंक सो कि हमें टाइम जो है वो मिल जाएगा. लेट्स सी, अगर तो कुछ थोड़ा सा जो है वो कर लें. बल्कि इस तरह करते हैं, मैं जो है वो बस चलो ब्रेक के बाद जो है वो थोड़ा मिल लेते हैं, क्योंकि आपको जाने जी जी बताएं दोबारा. Oh, okay, okay. So we are going for a break, for a 15-minute break, not more than this. ठीक है, 15 minute we are going for a break, and after the break we'll discuss, just summarize this whole lecture, and then we'll move towards the quiz. ठीक है ना? So मैं इसी दौरान I'm in the meanwhile I'm just uploading the quiz. Okay?
ठीक है
सर. ये क्विज नेक्स्ट वीक नहीं देते सर?
नहीं नहीं यार, नेक्स्ट वीक नहीं, नेक्स्ट मिनट भी नहीं लेता, अभी लेते हैं ना. जब एक चीज नेक्स्ट में चली जाती है, तो फिर जो है वो नेक्स्ट जो है वो कोई एंड उसका नहीं होता. ठीक है ना?
तो सर वो फ्रेंड्स की आईडी ज्वाइन कर दीजिए, तो उसने कहा कि सर को बोला था नेक्स्ट वीक लेंगे.
नहीं नहीं, वो नहीं हो सकता. फ्रेंड्स को जो है वो उनके ड्यूज का अगर मसला है, आईडी ब्लॉक हो चुकी है, तो ये कल की उसमें भी हुआ था. सो चूंकि आई एम गिविंग टू यू one chance to you, so if it is missed, then don't worry, you will have to take care of the next 3 quizzes. Okay, don't worry about this. ओके जी, ब्रेक का टाइम खत्म हो गया। आप मुझे सुन सकते हैं? कैन यू हियर मी?
Yes, sir.
Okay. अच्छा, okay, so we are discussing the stress transformation, and let's summarize this whole story. So stress transformation equation, we develop these three equations as our first step, and these are the orientation: sigma x, sigma x prime, sigma y prime, tau x prime, y prime. So these are the positive direction. Theta is a positive, so these are the positive direction. Okay, so these are the transformation equation. Then we develop principal plane and principal stresses. We develop expression for the principal. Theta n is equal to this one, and the normal component is this one, and theta s is equal to this one, and the maximum theta s is the maximum shear stress plane. So this is the orientation. Okay, so these are the orientation of these stress, these particular planes. And then we talk about the angle between the two, theta n minus theta s, and the tau maximum, and the stress invariant. We talk about the stress invariant. So this is the whole summary, and this I've summarized all the equations in these two slides. Again, you'll have to, you can pick any appropriate equations and then get the solution done. Okay, so this is the whole story, and since we are late, you'll have to complete your assignment, your quiz within 30 minutes. So we just have 30 minutes, a few minutes more. So let me ask the TA, अभी time जो है वो क्या हुआ है?
26, 10:26.
मेरी घड़ी में है 10:26. एजाज था घड़ी किस टाइम दे?
सर मां सर 10:30 थी सर।
10:30 था घड़ी के। हाँ, so we should start it, क्योंकि मैंने टाइम इसका जो है वो दिया है। पता नहीं है क्लासरूम जो है वो कौन सा टाइम कंसिडर करेगा, कंप्यूटर का ही करेगा। सो आप जो है वो उसको, चलो मैं ही असाइन कर लेता हूँ, आपको असाइन हो जाएगा। मेरे उसमें, मेरी घड़ी में जो है वो 10:27 है। सो आई एम गोइंग टू असाइन। चलो जी, आपको क्विज जो है वो असाइन हो गया।
सर टाइम कितना है?
टाइम 30 मिनट्स इंक्लूसिव ऑफ सबमिशन एवरीथिंग, और गूगल क्लासरूम पे सबमिट करना जरूरी है। सो इट्स मैंडेटरी, यू विल हैव टू सबमिट इट ऑन गूगल क्लासरूम within the 30 minutes, and you will have to make a proper PDF, a single file PDF जो है वो बना के उसको सबमिट करना है, ठीक है ना। कैम स्कैनर से PDF जो है वो पिक्चर्स और वो चीजें एक्सेप्टेबल नहीं होंगी, क्योंकि वो फिर मार्क नहीं हो सकती, ठीक है ना। सो आपने PDF जो है वो सबमिट करना है। चलो जनाब, अब आप जो है वो अपना काम एहसास द रिकॉर्डिंग स्टॉप कहा